All right. Thanks everyone for tuning in to the Corundum developer meeting today. All right, so let me go through the status update slides I have. I don't have all that much, so this hopefully won't take very long, and then we can get into discussion. All right, so announcements and status updates, not a whole lot going on. Announcements, the next Corundum developer meeting is going to be June 5th, and the next Switch developer meeting is going to be May 29th, assuming I checked my calendar correctly. Yeah. Okay, so getting into the status update summary. We got a couple bugs that we've been chipping away at. I guess maybe I should probably add one more point here for another potential PCI Express issue that we've been sorting out with the folks at MLE, but I forgot to add that. I'll talk about that a little bit though. And then also a little bit of updates on the queue management stuff. I did manage to resurrect the previous completion write back code, and it's working, but needs a few updates or a few additional updates and modifications. Signs of life, but step by step. All right. So the first bug that I've been working on is the DMA write done mux issue, and this one basically interleaved operations on different ports on the same segment on the internal DMA RAMs, but with a significant difference in delay, can cause a hang. And this I was able to replicate this in sim by adding a bunch of delay on the write done signal in the interface level. Basically, what I ended up doing is kind of introducing an asymmetry between the control path and the data path. And this uncovered the problem, which had to do with reading out stuff from an internal FIFO that maps which ports the reads came from, such that the write done pulses can be returned in the correct order. And this has been fixed in the development repo. The initial version, which I think I talked about the last time around, had an additional cycle of latency on the write done path, but the updated version has the same latency as the old one. So it shouldn't affect the performance at all. It's just removed the hang. So that's a good thing. So that should be fixed now. While I was debugging this, I discovered another bug. After adding that delay in the write done signal, I dropped the design on the hardware. I was intending on removing the delay. I didn't, and I got a hang. I originally thought that the new write done mux code was broken in some way, but I eventually traced that back to there was something else wrong in the DMA interface module. So the delay on the write done signal was causing the DMA interface module status FIFO to fill up, which was resulting in back pressure through the completion TLP path to the PCI Express hard IP core. And I was observing corrupt completions on the RC streaming interface coming out of the hard IP core, but all the handshaking looked okay. So it looked like there wasn't anything wrong in the shim. It's not like I was decoding the TLPs correctly, but the TLPs coming out of the hard IP core were screwed up, which is not good. They were screwed up in the same way as the completion buffer management issue that I had observed earlier and thought I might have fixed by adjusting some of the flow control settings. But seems like that wasn't the case, and that there's something else going on here. So one of the things I was thinking that might be going on is just that the completion buffer is being screwed up in terms of the logic inside of the hard IP core not handling something correctly. So one possible fix that I was thinking of implementing before is basically to use the hard IP core to assign the tags, and that if you don't have a tag assignment, you can't send the request. I'm not sure if that would necessarily solve the problem, but it also requires quite a few modifications. But then I realized that maybe there's another approach to this, and what I went ahead and did is I implemented some simple logic in the DMA interface module to keep track of kind of the total amount of outstanding read data. So every time you issue a read request, it basically accumulates the length of that request. and then you can specify a limit for how many, how much read request data is allowed. And it won't allow new requests to be issued over that limit. So I set a 64 kilobyte limit, still got a hang, dropped to 32 kilobytes, and seems to be working. So I haven't done a huge amount of extensive testing. I did kind of add a few more stages to my additional delay just to see if that causes any additional problems, but so far I haven't seen any hangs. So I think that's a start anyway. And I've gone ahead and implemented this in the upstream development repo. So we'll see if this actually solves the problem going forward, or if I have to go back and actually implement the tag management in the hard IP core and actually set things up to go that route. We'll see. Hopefully I don't need to go that route. The other thing I did as well is I'm testing this additional delay code on a couple of other boards. I tested it on the none of the DE10 Agilex, on my Agilex F series dev kit from Intel, and didn't see any issues with that. So I wasn't expecting to see any issues, but just to rule out, any sort of weirdness in terms of the back pressure, that one seems to work okay. Later today, I'm going to try, well, hopefully today, maybe tomorrow, we'll see. I'm going to try it out on the Stratix 10 MX dev kit and see if I can replicate any strangeness. Because this is something that MLE has been having some weird issue with the Stratix 10 boards, and it's unclear if it's, again, like a shim level issue, or if there's something weird going on in the hard IP core in the H tile. Wouldn't surprise me if there's a problem in the H tile, but if there is one, I don't know how we're going to work around it. So, but we got to isolate that. So I'm going to try that out and see if adding additional back pressure makes any difference there. And then also try it out just kind of, with the original, with these adjustments removed, and see if just normal, if we have any problems there. So that's my plan. We'll see how it goes. All right, now getting on to the new queue management stuff that I've been working on. Well, I was working on it until I got sidetracked trying to sort out these bugs. So I've done several things kind of to work up to reworking the completion write logic. So this includes implementing the new register layouts that I talked about before, and then also merging the TX and RX CQs into a single kind of CQ type, which hopefully will simplify things when it comes to implementing the updated completion write logic. And I also went ahead and split the completion event writes in separate instances because we're going to have a more complicated set of write back logic for the completions, and then something much simpler for the events, which hopefully events, you're not going to be generating so many of those that you need to batch them and write them back in big blocks. You do need to do that for completions if you have a big, high packet rate. But for events, it probably makes sense actually not to batch those, such that you have lower latency with generating interrupts and whatnot. Right, and then I also resurrected the batch completion write back logic that I put together previously. And with that, I went ahead and I updated the register layout so it matches the older completion handling stuff that I'd upgraded. And then I also went ahead and replaced the pointer write back logic. I pulled all that out and replaced it with the phase tag bit for improving the communication between the driver and the hardware. And I went ahead and implemented that in hardware. It works. The performance is slightly improved for a medium number of queues, but slightly worse for a large number of queues. So I'm going to take a look at the code in more detail, and I've got a few ideas for what I can do to improve the performance. It's a little bit of a rewrite, but you got to do what you got to do. And then after that, the next step will be taking a look at the kind of descriptor side once I get the completion side hammered out. I do have a couple of graphs here from the testing that I've done. So this is kind of a baseline test on the Silicon board with the MTU 1500 in my dev machine. And then with the new queue management logic, or the new completion right logic, for the most part, these curves stay about the same, but there is, I think, a relatively significant difference in the TX performance. I guess we're getting the peak at about the same spot, but it drops off a lot more with more iPerf processes. So what I think is going on here is just kind of a cache management issue where, as you have more queues active, stuff's being evicted from the cache more often, and we're getting less batching, which definitely doesn't help, but it shouldn't hurt all that much. But I think the other thing is that it takes a fair number of cycles to evict something from the cache and perform the write back and whatnot before that entry can be recycled. So I think part of that has to do with just some contention inside of the updated queue management logic. So I'm going to see about reworking things a bit to reduce that contention. So we'll see about that. Hopefully I can get these to look the same. Hopefully it'll be even better, but looking the same is a start. And then for MTU 9K, this is, I think, is going to be more limited by just the main DMA engine. The simultaneous TX and RX definitely changes a bit, but these can bounce around quite a bit. I'm not exactly sure everything that influences these. They end up at about the same spot if you look at kind of the difference between the two. But one thing I did notice is that this breakaway point up here moves from about 10 to about 12 iPerf processes. So I think we are potentially getting some benefit from the batching, where that's reducing some of the overhead over PCI Express. So that's some progress. But again, the main thing to notice about these guys is that we're not seeing any significant performance drops with the new completion right setup. So that's always a good thing. So that about rounds out the status updates that I have. And then there was some question about test equipment relating to debugging some PCI Express related stuff and whatnot. So I figured I would just go over some of the test equipment that I have really quick here. And this, I may be able to provide remote access for some of this stuff for debugging various issues with Corundum. So the first one is the PCI Express protocol analyzer, and this is the one that I have. It's an Agilent N5306A unit. So it's got two of the N5306A-A16 analyzer cards, and these cards are, well, the A16 license is for Gen 2 and 16 lanes. You need two cards for 16 lanes. One card can only do 8 lanes by itself. And then I have the N5315A-A16 interposer. So with that, you can probe all 16 lanes just with a normal PCIe card. You don't need to have any special probing sites or anything like that when you're using the interposer. So this can do packet capture and decode for PCIe Gen 2 by 16. Not much else to say about that. I can pull up the instrument. We can take a look at that in a minute. I also just literally this weekend received another piece of PCI Express test equipment. It's actually from the same kind of series of equipment that Agilent made. It's an N5323A so-called jammer card. And this basically allows you to inject various errors in the PCI Express link. Unfortunately, this card is only an A04, so it's only Gen 2 by 4, which is not great from a throughput perspective, but I think the widest that these cards even went is a A08 with 8 lanes. So they didn't even make a 16-lane version of this card. So that's not particularly great, but I think the idea with this one is, not necessarily to run it under heavy load, but to inject errors like, dropped TLP or a poisoned completion, something like that, and make sure that everything is handled correctly. So I haven't had any time to play around with this yet, but potentially if we get it set up, might be able to find some additional bugs in the DMA engine or something, and it could be useful. I know the Xilinx devices, the hard IP cores in there track the completions and can detect timeouts. If a completion or request gets lost. The Intel devices, I don't think do that. They might have some mechanism for reporting it, but I haven't taken a close look at how that works, and I don't have it implemented yet. But this jammer card would allow us to test that for both the Xilinx and the Intel devices and make sure that everything's handled correctly. So, because it's one thing with the test benches to test some of these things, which I think even right now I'm not really testing too many of these corner cases. But it's another thing to actually include the actual hard IP core and make sure that all of the interfacing and whatnot is working correctly and doing what it's supposed to do. So anyway, that should be, I think, a pretty useful tool. And then finally, I picked up a Viavi ONT603 network tester unit. It's a 100 gig capable network tester. It's got the dual CFP2 card, so it's actually 2 ports at 100 gig. It supports 25 gig, 40 gig, 50 gig, and 100 gig. Although there are some, limitations and provisios on a couple of those. The unit has the CFP2 slots for 100 gig, so that has to be adapted in some way to QSFP28 to actually connect to, some piece of hardware that you want to test with. So the solution that I found that seems to actually work is to just use CFP2 optical modules and then cross-connect that with an LR4 QSFP28. So that works, but there are some limitations. Like if you want to do something at 25G, I'm not sure the best way of handling that. I mean, obviously, if you have a QSFP28 and you're just using the first lane for 25G, that's fine. But if you have a card with like an SFP28 slot, well, you can't fit a QSFP28 in there. So there's a question of, how we might be able to connect an SFP28 module to some sort of CFP2 module. I haven't totally figured out a solution for that that I think is going to make sense. But anyway, something to do some head scratching over, maybe a little bit down the road. And I have tested this thing with Corundum as well, and I was able to get a link up and blast packet traffic into Corundum at 100 gigabits per second. The nice thing about this tester is that it uses FPGAs to generate the traffic, so there's no problem with generating, minimum length frames at 100 gig line rate, all day long. Corundum's not gonna be able to handle that. It's not really designed to do that, but I think this could definitely be useful for, testing the switch design to make sure that everything works correctly. And for larger MTUs, it could definitely be useful for testing Corundum. Anyway, we can take a quick look at all of these devices real quick once I close down my slides here. Okay. Let's see. So this is the PCIe protocol analyzer that I have. 2-slot mainframe with 2 of the N5306A cards, and then we have the interposer card over here. And this one, pretty straightforward setup. That goes in the the host slot, and then you can stick a card in here, and then it's got the analyzer cables that go around to the actual analyzer itself. Pretty simple setup. This communicates with a host control computer via Ethernet, which is kind of a pain in the butt. This thing is actually net booted. So you gotta have a dedicated NIC and a DHCP server and a TFTP server all set up on the control host for this thing to work. It's kind of a pain, but it does work. So I guess the other limitation of this thing is it is a rather old analyzer with Gen 2 support only. So that does kind of limit what you can do with it, because if you can only repeat your issue at Gen 3, well, and it disappears at Gen 2, then this analyzer is probably not going to help you pick it up. But it does come in handy occasionally. And part of the usefulness of something like this is that I think it captures something like 2 GB per card worth of trace data. So if you have some weird issue going on, you can capture quite a lot of trace and hopefully isolate what's going on. So the other interesting thing about this, I mean, comparing to something like Wireshark that also captures packets in a similar way, this is doing a physical layer capture, while Wireshark is just capturing, the actual, payload data without anything at the physical layer. So basically, PCI Express Gen 1 and Gen 2 is 8B10B encoded. So this is literally capturing the 8B10B control characters. And then the software looks at those and extracts the TLPs and DLLPs and everything else from the physical layer capture. So that's the kind of cool thing about this is you can actually look at, the flow control credits and other stuff, which, you wouldn't be able to see if you're just looking at the TLP packet data. And actually, I guess that is one difference or one advantage of using something like this over the ILA. It's like usually when I'm looking at PCI Express stuff, I'll just use the ILA and look at the internal interfaces on the FPGA. But this potentially gives you a much deeper capture buffer, and you can also look at the flow control credits because maybe there's something funky going on with flow control, being released at a weird time or something. I think for what we're doing, since we're not actually building the PCI Express hard IP core itself, we're just working at the transaction layer, this is not probably as useful as it could be. And if you are building that, then you probably need something that's actually running at full speed. So I don't know. I've not gotten quite as much use out of this thing as I might have hoped. Right, that's the protocol analyzer, and then I've got the jammer card here. Actually looks very similar to the interposer card, just in terms of the overall shape. The N5323A. So again, you put your card up here. This plugs into the host machine, and then there's a USB connection for control here. So with this guy, I think there's an FPGA under this heatsink. It's probably similar to the FPGA in the analyzer cards. But the PCI Express traffic goes through there, and then you can use the control software to set up various error conditions, basically, that this thing will insert. So, and then this one only supports 4 lanes. They routed off the rest of the connector. You can actually see on the board where the traces are for the 8-lane version of it, but they just cut off the rest of the connector. That's always annoying when I see stuff like that. It's like, dang it, if they didn't route that off, maybe. Oh well. So we'll see. This could end up coming in handy. And then finally, I've got this thing over here, which is the network tester. It's a dual port CFP2 version test cards right up here. These things are pretty impressive looking test cards. Let me see if I can pull this thing out of here. But yeah, this thing can do line rate traffic at 100 gig and at 40 gig, 25 gig. Can't do 10 gig, which is kind of annoying. So yeah, there's a lot of stuff on there. The interesting thing about this is each card has its own little embedded PC, and all of the control is done basically through a Java application through the web browser, which is makes remote control easier because it doesn't matter, if you're running that on the analyzer versus running that on an external machine. So yeah, it's got the 2 CFP2 slots on the front. It's got a pair of QSFP slots as well. But they're QSFP pluses, not QSFP 28s. So if you're running at 100 gig, you got to put the modules in the CFP2 slots somehow. Yeah, and then on the back, we got 2 big honking FPGAs under these heat sinks. As far as I can tell, this thing uses Stratix 5 FPGAs. I didn't even realize Stratix 5 had 28 gig capable SerDes, but I guess it does. So presumably the newer ones that they have are going to be using more recent parts. This one, I'm not sure how many years old this analyzer is. It's or this mainframe and test card are. It's a few years old though. Anyway, this should be, I think, mainly useful for testing switch design, but certainly it can potentially be useful as well for testing the NIC. I'm not going to lose caps off. Okay. So that's about all I got here to talk about. I don't know if you guys have any questions or comments or anything you guys want to discuss.
Well, I have never used any equipment like that, so for me it's kind of new.
Yeah, me neither. I think it'll be fun to play around with.
Yeah, I find it very interesting, and also, yeah, maybe we have the chance to test it in a few weeks.
Well, yeah, when you get here, we can definitely fire it up. I guess the real fun part is when we actually have the Switch at least partially working. We get this thing hooked up to it, and
Yeah,
hopefully root out some bugs.
yeah, definitely.
Yeah, Joachim, I don't know if you guys had any other questions about the PCI Express protocol analyzer stuff. I know you guys asked a question about that, or I guess it was Ulrich. I have been taking a look at eBay just to kind of see what sort of analyzers are available because I would kind of like to get a Gen 3 capable one, but there doesn't seem to be very much available this type of equipment. Um, there are a few of the Gen 2 ones, but honestly, it seems like the hard part is not so much finding the analyzer, but finding the accessories. So it's like I've even seen a couple of the Gen 3 ones from LaCroix, but just the analyzer, no accessories, right? So if you don't have any of the probes or interposer cards or anything, the analyzer kind of isn't very useful. Although right now it does look like there are a couple of the Agilent ones on eBay, not 16 lane ones, but 4 or 8 lanes, something like that. So,
Hmm. And I guess another question is the software itself to make use of the device.
is that available? Yeah. So for that's definitely something to worry about.
Or a license question, most likely.
Or licenses. Yeah. Okay. Right. So that's one thing that I was worried about when I first got this thing. The licenses that they talk about are burned into the cards, right? So if you buy a card, that will have the license built into the card. And it kind of the card acts as its own dongle, basically. You don't need any additional stuff. You just need the software. For the Agilent ones, at least, for these older ones, the software could be downloaded from, well, I guess a Keysight website now. And then you kind of have to figure out how to configure everything when you install it, but it is at least available. Since I think they haven't updated the software for this thing since I picked it up a few years ago, but this thing is quite a few years older than that. So, that's the downside about that. But for the ones from other manufacturers, yeah, that I guess could definitely be a problem. Like for the LaCroix analyzers, I'm not sure what the story is with software for those. Although I haven't really looked into that because I haven't seen one that was complete enough to actually warrant, purchasing. There are a couple of Viavi analyzers that I saw on eBay. But yeah, I'm not sure what the story is of software on those. I think one of the listings had like a flash drive in it with software on it. So, that's useful. But yeah, if you want to get the latest stuff from Viavi, I don't know, you'd probably have to talk to their support and probably get a support contract or something. I don't know. That's definitely something to be worried about. That was one thing I was trying to figure out with this guy as well, because the software on there is a couple of years old. It would be nice to get a newer version of it. I don't know if anybody has any contacts at Viavi or has a similar analyzer and has access to their download site. Maybe we can cross that bridge later if somebody knows anything about that. But at least the nice thing about this one is actually all of the software is on the analyzer. So, it's got its own built-in control computer and whatnot. And I guess, like I said, everything is done with Java through the web browser. It uses the Java Web Start or whatever to run everything. So even
great.
internal thing, it's it has advantages and it has disadvantages, right? I mean, Java's a real pain in the butt. You can definitely tell. Well, it's also the processor in this thing is not the fastest, so it's pretty laggy as you're using it. But ostensibly, you should be able to run that on whatever computer that you have connected to this over the network, and run the control software there, without having to go hunt down install CDs. And because that's one of the annoying things about like the protocol analyzers from Agilent is that the software only runs on like Windows 7. So, and I was having issues with my VM too. I originally set up a VM for that software under VirtualBox. And then, well, VirtualBox is Oracle. So, yeah, trying to avoid using VirtualBox. So I migrated the VM from VirtualBox over to the standard Linux KVM virtualization thing. And then the software didn't start. It gave me some weird error messages. I'm like, what?
Okay.
What difference does the VM make? So I don't know if it was the software itself that's a problem or something else. Like if you do a fresh install under KVM, maybe it would work. I'm not sure. I haven't spent any additional cycles screwing around with that because I just fired up the VirtualBox VM and I'm like, all right, this is good enough. But if we might set something up like this for remote access, maybe I'll actually get an old laptop and just install stuff directly on there, and then we can use VNC or something to control it. I'm not sure, especially if we're also using like the jammer card and whatnot. It might be more convenient just to plug everything in than to use USB forwarding. I guess the other thing about this particular analyzer is that the control is over Ethernet, so that's not too bad. I think they're newer Gen 3 ones. They're like they go into their AXIE chassis, and that's actually PCI Express. So the host machine has to have, a PCI Express card in it. So for desktop machine, that's not too bad. For laptop, I mean, I guess you gotta go in through the Express card slot, but I'm not even sure where you get the appropriate Express card with the right connector on it that'll plug into the mainframe. They exist, but good luck getting one. And that's just in addition to getting the analyzer, the interconnect cables, and the interposer card and everything else. So yeah, definitely assembling one of these things with all the accessories such that it's actually usable is not so straightforward, especially if you're on a budget.
Yeah, that's always the problem.
Well, the prices have been inching down on those couple of Viavi analyzers. I think they were originally at like 9K, now they're at like 7K. So give it a few more months and maybe they'll be affordable. But yeah, still, software is definitely a significant question for that. I don't know if they have a similar setup to this thing where it's just done through the browser, or if you got to get the software from Viavi or from a flash drive or from a CD or something else. It's always annoying when they lock the software behind their support contract. It's like software's useless without the hardware. So why can't you guys just make it available? Viavi also is one of those annoying companies that doesn't really have any useful public documentation about anything, and they also hide the documentation for old stuff. Like from browsing their website, I can't find any links to this thing, right? I can find links to their newer 800 series, but not the 600 series, even though that's supposed to be, I think, like if you download the latest version of the firmware, it does work on a 600 series. They still have a 600 series firmware available, recently released. But yeah, you can't find even sales brochures for these things. It's like, really? What are you going to do? Anyway, anything else that people wanted to discuss? Or I guess there's not too many people connected to the meeting today, so
yeah, perhaps an ad hoc question
yeah, sure.
Regarding our current problem, where it turned out to at least be a workaround to disable the extended tag support.
Oh, right, yeah.
Before I went that route, actually, to just disabling that, we started to build designs with a TX limit parameter of the DMA interface. decreased down to even 1. It starts with the default setting is 64, I think, which depends on the width of the sequence number interface.
Right.
And we reduced the TX limit even to 1. And I'm still wondering, there seems to be...
So the thing to understand with the TX limit is that this is not limiting the number of in-flight operations. This is just limiting the number of in-flight operations inside of the transmit path. So once it hits the bus and leaves the hard IP core, then you can issue another transmit, right? So even if you set it to 1, it's not like you can only have 1 outstanding operation. You can have a whole bunch of outstanding operations, but only 1 in the transmit path.
But still, I mean, shouldn't there
you're still
be
running into the issue, or
still running into the issue, and the performance? I mean, it depends on how you run, and if you make it to the limit where the issue does not hit, we essentially reach the same performance. So there's no performance degradation even when going down to a TX limit of 1. That was a kind of a surprise. So I expected that the performance would be at least lower, perhaps not significantly lower, but it seems to be the same. So the question was, well, is TX limit doing anything at all?
Yeah, it's possible on the Intel devices it doesn't really do much. On the Xilinx devices, the idea behind the TX limit was it's related to how the hard IP core works on those devices, because it has its internal little completion buffer. It won't release read requests if it doesn't have buffer space available, but it actually has a small amount of buffering for the read requests themselves. So it'll store up to like 12 or 16 or something read requests inside of the IP core, and then it will release those as buffer space becomes available. So the point with TX limit was to make sure that we don't overflow that buffer and then cause the RQ interface to block, which would then prevent write requests from going out. So I implemented it originally for the Xilinx devices. So with the Intel devices, it's not really doing anything useful because the Intel devices don't do that. They just send everything. Or at least I don't think they do that. So I'm not sure it's going to have much impact on the performance. I mean, obviously, reducing it has the potential of reducing the performance, but even if you set it to 1, it's not like limiting you to only using 1 read request or something.
Yeah. Okay, understood.
So if the read requests are going through the pipeline, well, I guess the other thing too is by transmit path, it's specifically referring to when the requests and the completions get merged together. So once the requests and the completions are merged, then you can't have like a register read operation take place before a DMA write takes place. So it's not even the entire transmit path, it's just up until that merge point. So with the Xilinx devices, that merge point occurs in the hard IP core. In the Intel devices, it occurs in the shim. So you actually get the sequence numbers returned quite quickly when that merging takes place. So with the Xilinx ones, I think there can be a relatively significant delay between when you issue the operation and when you get the sequence number back when it gets sent. With the Intel ones, well, the shim is returning the sequence number, so potentially it's only a few clock cycles.
Okay.
So, you can certainly lower that one, but it's possible it's not going to change much of anything for either the RX side or the TX side. But I did add the but you might try out the latest version of the PCI Express DMA engine, because I've added a couple of things. I've added status bits for RX and TX, or for just to indicate that it's busy, that something is running. I'm eventually going to wire that out to a register block so you can read that and check to see. So when something hangs, you can go, oh, it's the DMA engine that's stuck.
Okay.
Versus something else. And I've also added this parameter that allows you to put a limit on the amount of outstanding read data. So that one you can definitely play around with. And if you set that too low, it won't be able to issue any operations. But that,
okay.
That will definitely also limit the performance, but it limits it in a different way than lowering the number of tags, right?
Yeah.
Because each tag can correspond to a different amount of data. So by lowering the total amount of data that you can have in flight, that's potentially going to be a narrower change with less impact on performance than just reducing the number of tags, right? Because for tags, you need one tag to read, at least the way things are set up right now, it requires one tag to read each descriptor. So if you reduce the tags too much, that's really going to impact the performance. But by putting a limit on the amount of data, well, that will allow you to read a few more descriptors if you need to, but it will limit the kind of amount of outstanding data. So that's certainly something to play around with. But yeah, I think probably the most important thing to do is to take a look at the both sides of the shim, basically, and make sure if we're seeing a missing completion, did it get dropped in the shim or did it get dropped before the shim? Figure out where something got dropped. So
yeah, we have already
probed that yet, but
we are working on it, and
okay.
I hope to have some data by now. But unfortunately, Quartus and Signal Tab I don't know, angry at us. Crashing all the time and so forth. So hopefully by tomorrow we should be able to say, okay, is everything okay there, or no, we see a difference there.
Right, because it's entirely possible there's some sort of bug in the shim that we got to sort out. I know one thing that's weird about the Intel devices is there's a ready delay on there. It's like with AXI Stream, ready and valid, same clock cycle. Either they're set and stuff gets transferred, or one of them is not set and stuff doesn't get transferred.
Yeah.
Very easy to debug if that's wrong. With the Intel devices, there's some stupid delay on the ready, right? So ready drops and then you can keep sending for some number of cycles.
This is a property of the Avalon definition.
Yeah. Yeah. And if you don't have that ready delay right, then everything gets screwed up.
Yeah. Okay.
I think I have it right, but it's possible that's wrong. And if that's wrong, then you're going to get all sorts of weird behavior if the shim tries to exert back pressure against the IP core. So, that kind of stuff needs to be double checked. I thought I checked. I mean, I haven't noticed any weirdness with that. But then again, I also don't know if that ready line ever gets deasserted in the hardware. I do know that, my test benches test that, but it's entirely possible that the model I have is set wrong. So, because figuring out what number to put in there is definitely, counting cycles in the timing diagram in the data sheet to make sure it matches what I'm seeing in the simulation. I'm like, okay, if that matches, then I guess we're good. But, we'll have to check it out on the actual device and, make sure everything looks good there. So, yeah, I mean, if that's the problem, then that's a simple fix. But if something else is going on, we'll see.
We did another experiment on this way to perhaps find a quick workaround. And the next thing was to limit the operation table size of the DMA interface. This I thought should also have an impact on how much the MQNIC side of things can have in flight requests in flight towards the DMA interface. And I reduced it to just 2. I guess just a table size of 1 is currently not supported. And again, just kind of for your information, does not help. The issue is still there. So currently I'm running with a TX limit of 1 as far as that goes, and an op table size of just 2. And the issue is still occurring within seconds. Yeah, that was the latest experiment. now.
Well, op table size 2, but do you still need all 4 of the interfaces turned on, or is 1 enough?
That's a good question. I'm usually driving all 4. Yeah, I could test and see if now perhaps just 2 suffice or something like that. Yeah.
I'm just thinking with an op table size of 2. I mean, that's 2 read requests,
Yeah.
right? So seems like that should be present even if you just have 1 interface active, right? Because how many read requests can you issue? Right, to read, it's already going to be trying to read multiple packets even with just 1 interface.
Yeah.
At least that's what the transmit engine tries to do. So that's a real head scratcher. I mean, that's, yeah. So I mean, what doesn't make sense to me now is that even taking op size down to 2, that should, limit the number of tags that's being used as well, right? To, I mean,
Yeah.
not
Yeah.
necessarily far below 32, but that should, I would think, have an even bigger impact than disabling extended tags. But when you said you disabled extended tags, you didn't see the bug. So
Right. Yeah.
that's weird. That's really weird. Well, the other thing I will
And
mention about tags as well is, you were wondering about tag space. The core preferentially uses the 32, the first 32 tags over the other tags. So once it's used all of those 32 tags, they're all in flight, then it'll start using the other tags. So if you limit the number of operations to 2, and each of those operations takes less than 16 tags each, you're never going to use more than those initial 32 tags.
Are you sure that these first 32 are really have such a preference? Because in our
no,
dump,
so this has to do with how the how enabling and disabling extended tags is supported. So there's 2 different FIFOs to store the tags. One FIFO stores the first 32 tags, the other FIFO stores the rest of them. And the logic pulls preferentially from that first FIFO that stores the first 32 tags. Only when that FIFO is full does it pull from the other FIFO.
Okay. From the capture we've done, which was mentioned by colleague Tobias, from this capture, it seemed like that all tags are kind of used in a round robin fashion, as if there was just one FIFO, but perhaps there's just the capture is perhaps too short to see the effect.
Right. Well, I mean, it takes some time for the operations to complete, right? So you can have a lot of read requests in flight. So if you have all the first 32 in flight and you're just looking at the higher number ones, then it's going to look round robin. In fact, it might even look, well, I don't know if it would look, yeah, it's just whether you get reordering or not in the order that the tags are used depends on, how they complete from the standpoint of the host. So I don't know if the system that you're running in is going to reorder the completions or not, to the point where stuff gets reordered in these FIFOs. In the old version of Corundum, or of the DMA engine, initially I did use basically priority encoders to enforce a round robin use of the tag space. But that was not great from a timing perspective, and just dumping them in a FIFO seems to work better from a timing perspective. Although the flip side is then it's not necessarily going to be a perfect round robin, but I think that doesn't really make too much difference. So, but yeah, initially it's going to look round robin until you start getting, reordering, and then slowly it will diverge. But yeah, the key point that I was just mentioning is that, the first 32 are handled differently from the rest of them. There are 2 different FIFOs, and the first 32 are prioritized over the other ones. So if you're using less than 32 tags, it's only going to use, the first 32. It's only if you use more than 32 tags, then it will start using tags from the other FIFO. And when that happens, then it does use all of them. But I guess it sounds like you haven't played around with the tag count. because you could try setting the tag count to 64 or 128 or something.
Yeah, that
See
was
if
the
that
next
makes any
idea. Yeah.
difference. Yeah. Because that was one thing that I was wondering about for one of the devices. Yeah, I guess that I think that was the Xilinx ones. Because there was another bug in the Xilinx hard IP core that had me going for a while when we first started using the segment interface. No, I guess this, I can't remember exactly what the lead up to this bug was, but the workaround was, well, we just got to use the segment interface because the for the by 16 interface, the non-segment interface, there's a bug in that shim somewhere, and enabling more tags was causing things to hang, because not because there were more tags necessarily, but because that was resulting in a higher throughput through the hard IP core, and it was screwing up the logic that was adapting between the segmented and non-segmented interfaces. So by using the segment interfaces, we worked around that bug. But yeah, I originally thought, well, maybe it has something to do with using these additional higher order tag bits. But it turns out that wasn't the case. And yeah, I'd actually written up a hacked up test program, which basically just hooked up the RQ and RC interfaces of the PCI Express core to just an AXI Lite interface, and then I just sent a bunch of cooked up TLPs with different tags and made sure all 256 tags worked. And they did, so I'm like, okay, well, that rules out that. Yeah,
okay.
well, I guess we'll have to see. Hopefully we'll be enlightened by what you discover with the signal tap probing on both sides of the shim. If it's a shim bug, then hopefully it's an easy fix. If it isn't a shim bug, then we have a problem.
Yeah, we'll see. Interesting. I just ran it again with Optable size 2. Just now, ran again. It didn't die. So obviously the probability is at least lower.
Interesting.
I'm usually running for 7.5 million or these 7.7 million packets. And okay, now it's really impacting performance. Whoa. Okay. Perhaps I have to say delete my comment before that regarding Optable size. I don't know how many bit streams I have laying around. Most likely I picked the wrong one. Sorry.
These things kind of accumulate after a while. Yeah. That having a significant performance impact, that would make sense. So okay.
Yeah,
but running the wrong bit stream, that would be an explanation for why you didn't see that. Okay.
Yeah.
Well.
Okay. I'll test all the bit streams I've built, 2, 4, 16, 32, and so on, and see which perhaps we then meet the point where the issue is showing up.
Possibly. Well, we'll see. Yeah. So the issue with limiting the op table size is that, you know, one operation could correspond to multiple read requests. So what's probably going to be more useful, I think, is limiting the tag space. But I don't know.
Yeah.
We got 3 knobs, right? The operation table size, the tag table, the number of tags, and then if we use the latest version of the DMA engine, then we also have just the amount of read data. So that one, honestly, is, in my opinion, is probably the most useful one to play around with, because that's going to allow you to use, you know, more or less tags as needed, depending on the size of the operations. But, you know,
the other gut feeling, which is kind of coming up, at least for me, is that this might have to do something with the newer root complexes, the newer CPUs, because we can reproduce the issue with a kind of a current CPU. It's an i9 11900K, so the 11th generation, and we also have an AMD one, I think a rather new one, an EPIC 7200 something. And the issue is not occurring there. And I think that the performance of both machines should be similar. And but so I'm wondering,
well,
perhaps
so one
it's
thing
a
to take a
specific.
look at. Yeah, one thing to take a look at whenever you have different machines is just LSPCI and see if there's any differences in terms of how the card has been configured. So the max read request and max payload sizes sometimes change depending on the machine you're running on. A lot of the machines I'm running on, they're 256, but I think some of the AMD EPIC machines I have here might set it to 512. So that potentially changes something. That's just something to look at.
That's actually the case also with this i9 CPU. It has a max read request size of 512. Yes. And what we see in the
max
capture,
read request size of 512, I think, is kind of the default, but the max payload size, one I've seen different numbers.
Right. Yeah.
So sometimes it's 256, but on some of the newer machines, they seem to be sitting at the 512. The max read request size, in some cases, you can kind of play around with that. I've definitely seen some servers that will set that to 4096, just max it out. And I'm not sure what kind of performance impact that has necessarily, but
by the way, now I remember it was before the weekend. I also reduced the max read request size to those 256 instead of 512 on this Gen 11 Intel CPU, and the issue still occurred. So I did that because we saw in the capture that it seemed like the completions which were missing are kind of the second part of a request.
Right.
And that's why I reduced it, but didn't help. I mean, that's also a little bit strange. Perhaps it's just a misinterpretation or not having all the data. But in the capture, we really see that the second part is missing.
Right, because that's always the downside of using something like the ILA or Signal Tap, or whatever. The sample depth is very small, so you can't look at very much trace. Stuff that might become clear if you have, several megabytes worth of trace.
On the other hand, all the completed requests which are in the capture occur quite next to each other, so clearly within the capture. And of course, it may be that this one read request is delayed by something and doesn't make it into the capture. But I don't know.
Yeah, I mean, it definitely seems likely that these things are getting dropped somewhere. But it's just a question of, so if we're seeing like kind of bursts of these things getting dropped, then that to me kind of implies maybe they're showing up in a batch and there's some sort of back pressure issue, handshaking problem. The first couple make it through, and then the handshake gets screwed up, in the middle of the batch, and the rest of them don't make it through. So I don't know. We're definitely going to have to take a closer look at the capture on the input side, just to make sure that the handshaking protocol is being correctly followed.
Okay.
Because I think if we can get a capture that, it might be pretty clear what's going on, right? If we look at the ready line and we look at the other signals changing with respect to that, we can check to see what the core thinks the ready latency is, and double check that versus what the shim is expecting, and probably need to fix the shim, but
we'll see.
Yeah, but I guess you guys got to convince Signal Tap to actually work as opposed to going on strike. So
it's really annoying. It's every now and then it even kills the JTAG D, the JTAG server. I mean, how is this happening?
Yeah, I don't know.
And then we
There's a lot of
really
people
need
that
to
say the Intel tools are so much better than the Xilinx ones, but I'm like, nah, they both
Yeah.
have lots of they have their own problems. They have different problems, but they have their own problems.
Yeah, I've never seen the hardware server, the Xilinx hardware server, crashing like this. Um, that's new, at least.
Yeah, I mean, yeah, that doesn't make a lot of sense because it seems like that the hardware server should be kind of disconnected from whatever the UI
Yeah.
is doing. The UI
Yeah,
crashes, well, I mean, the hardware server should keep doing its thing. It's a totally different process, but if that's
yeah,
not the case, well, they got some bugs.
yeah. And then my
Ah,
colleague says, "Yeah, I have to restart the machine." I say, "Why do you have to restart the machine? Why should the JTAG server even take the JTAG dongle down, which is connected to the machine, taking the machine down? What?" But yeah, he says that's a way to recover.
oh man.
Very, very strange.
Well, I mean, I guess the flip side is that even if you could recover some other way, at some point it's just quicker to reboot the machine and then you're sure you're coming back
Yeah.
with a clean slate.
Yeah,
Oh
definitely.
man. Anyway, hopefully this doesn't cause too many more headaches. Maybe we should get some aspirin, you know?
Ah, no, it's not that bad yet.
Yet, right. All right. Well, I'll keep me informed on Slack on Zulip how this goes, and as soon as you have a trace, I'll be happy to take a look at it, and I'll see if I can
Yep.
test it on my end and see if anything interesting shows up. Like I said, I ran it on the Agilex board, didn't see anything weird. I'm gonna try a couple things on the Stratix 10 MX board. Now that I've gotten that other PCIe issue sorted out, I'm gonna cycle through some of these boards and see if I can uncover anything. So,
Okay.
we'll get to the bottom of this eventually.
Yep.
All right. Well, I guess I'll talk to you guys in 2 weeks then, via Zoom, and hopefully significantly earlier than that on Zulip.
Yeah, sounds good. Thanks.
Okay, see you, Alex.
All right, sounds good. Talk to you.
Bye. Thank you.